So, in the last video, we have seen what are some inspection practices that are recommended by API 570. Now we'll build upon that. So the last section was again the heart of the code because it was related to inspection of various types of components in a piping system. But in this, we are more interested in what should be the interval and frequency of inspection. Because as we already know that we cannot do inspection each and every day because that will increase downtime. If we do it every day, then when we are going to work with that equipment, okay, because the inspection can be very intrusive. So we need to have a proper balancing act between the times that is needed for inspection and continued safe operation of the component. So API 570 section 6 builds upon this. So it is the scheduled inspection shall be conducted on or before their due date and may be considered overdue for inspection. Alternatively, an inspection due date may be determined through risk-based assessment in accordance with API 580. This due date may exceed the typical half interval used in more conventional analysis. So we'll talk about what is this half-life approach or what is RBI. We'll talk about this later on. The appropriate inspection shall provide the information necessary to determine that all of the essential sections or the components of the equipment are safe to operate until the next inspection cycle. The risk associated with the operational shutdown, startup schemes, and possibility of increased corrosion due to exposure to the equipment surfaces, to air, moisture, soil, any other thing, should be evaluated during the internal inspection shall be planned. This code is based upon monitoring and representative sampling of the inspection locations on the selected piping when specific intent to reveal the reasonable accurate assessment of the condition of the piping system. Inspection during installation and service changes. So whenever the pipe is getting installed, first we have to check it because this will be considered as the original condition of the pipe, and whatever degradation happens later on will be assessed through the evaluation of what was the original condition of the pipe when it was installed and what has happened after some years of service. Okay, so the original inspection is very important. It initiates plant inspection records. So piping shall be inspected in accordance with the code of construction requirement at the time of installation, because during at the time of installation it is not an in-service pipe, it is a new pipe which is generally governed by the construction code. In most cases for pressure piping it will be B31.3. The purpose of installation inspection is to verify that pipe is clean and safe for operation. To initiate plant inspection records for piping system, the minimum installation inspection include the following items: verifying that the pipe is installed correctly, correct metallurgy is used, supports are adequate and secured, exterior attachments such as supports, shoes, hangers are secured, insulation is properly installed, flanged and other mechanical connections are properly assembled, and the piping is clean and dry for operation. We also need to verify the pressure relieving devices satisfy the design requirements. That is, correct devices used, it is at correct set pressure, etc., and they are properly installed. The installation inspection should document the baseline thickness measurement. Baseline thickness measurement is the original thickness measurement. After that some corrosion happens, the corrosion is only going to be assessed based on what was the original condition. Okay. Next is piping service change. If the service conditions of the piping systems are changed, that is, will exceed the current operating envelope, that is process contents, maximum operating pressure, maximum minimum operating temperatures, inspection interval shall be established for the new service conditions, including the review of the applicable pressure relieving device settings. If both ownership and the location of the piping are changed, the piping shall be inspected before it is reused. Also, allowable service conditions and inspection interval shall be established for new service. Next is piping inspection planning. So obviously, before doing anything, a planning is important, because if you don't do planning, then we are just shooting in the dark. Okay, planning is always important so that you can understand that whatever your planning stage assumptions were, are they properly identified and controlled or not. So the frequency and extent of inspection on a piping circuit, whether above or below the ground, depends on the forms of degradation that can happen on a piping and the consequence of the piping failure. So what kind of damage mechanisms are associated with that piping system, and what would happen if the loss of containment happens? The inspection strategy based on the probability and consequence of failure is already, we know this, that this is known as risk-based inspection approach. The simplified pipe classification scheme in 6.3.4 is based on the consequence of failure. The classification is used to establish frequency and extent of inspection. The consequence assessment would be considered for potential for explosion, fire, toxicity, environmental impact, and other potential effect associated with the failure or the loss of containment. After an effective assessment is conducted, the results can be used to establish a piping circuit inspection strategy and define the appropriate inspection plan as per 5.2. Setting up RBI. So you can use this, or you can use again a risk-based assessment. So risk-based assessment, whenever we are using, we have to look out at the recommendations given by API 580, and that is how we are going to identify what will be the next inspection interval or the next inspection due date and the extent of inspection that is required. If we don't do RBI, if we don't have any risk assessment, then if the RBI is not used, the interval between the piping inspection shall be established and maintained by using the following criteria: corrosion rate and remaining life calculation, piping service classification, and applicable jurisdictional requirement. It is also based on the judgment of the inspector, piping engineer, piping supervisor, material specialist, based on the operating condition, previous inspection history, current inspection results, and conditions that are warranted for supplemental inspections covered in 5.5. Owner, user, or inspector shall establish the inspector interval for the thickness measurement and external visual inspection where applicable for internal and supplementary inspections. For class 1, 2, 3 piping, the period between the thickness measurements of for CML or circuit should not exceed half of the remaining life or maximum intervals that are recommended in the table 1, whichever is less. So this is table 1. This is the maximum recommendation inspection interval for different classes of pipe. What is class 1, what is class 2? We'll just talk about it in the next section. But depending on the higher consequence of failure, the more riskier the pipe is, it is going to be in a higher class. Okay. The Let's imagine if you have a fluid that is flowing inside your piping and it is at auto ignition temperature and it is located in a residential area or it is located in a high activity area, then the consequence of failure is very high. In that case, we might consider it as in a class 1. Okay. So more risky it is, the more severe the classification is going to be. Whenever the remaining life is less than 4 years, the inspection interval may be full remaining life up to the maximum of 2 years. The inspection interval is established by the inspector or piping engineer in accordance with the owner/user's quality assurance program. So this is the table. We'll talk about this table later on. The maximum interval for class 4 are left to be determined by the owner user based on the reliability, business needs, and jurisdictional requirement. For piping that is in non-continuous service, the inspection interval between the thickness measurements may be based upon the number of years of actual service instead of the calendar years. The inspection interval shall be reviewed and adjusted as necessary after each inspection or significant change in the operating conditions or inspection results. General corrosion, localized corrosion, pitting, environmental cracking, and other applicable forms of deterioration mentioned in 5.5. So we have seen in 5.5 there were various kinds of damage mechanism which the piping was subjected to, and API 571 shall be considered when establishing the various inspection intervals. Next is, what are service classes of a pipe? So owner user shall maintain a record of process piping fluids handled, including their classifications. There are 4 classifications listed here. So class 1. Class 1 is going to be the most dangerous piping if the failure happens. So services with the highest potential of resulting in immediate emergency should the leak occur are in class 1. Class 1 includes flammable services that auto-refrigerate and lead to brittle fractures, pressurized services that rapidly vaporize, forming a explosive mixture such as C2, C3, C4 streams, fluid that rapidly vaporize and are those within the atmospheric boiling temperatures or where atmospheric boiling point is below the operating temperature, hydrogen sulfide greater than 3% weight in a gaseous stream, anhydrous hydrogen chloride, hydrofluoric acid, piping over the adjacent water or public waterways, flammable services operating above its auto ignition temperature, all of these will be considered as class 1 piping, which is going to be very risky. The thickness monitoring for class 1 is to be in five once in a 5 years, and external visual inspection also needs to be done once in a 5 years. This is given in table 1. So table 1, class 1 is 5 years, thickness measurement, visual inspection is also 5 years. So once in 5 years we might need to do this for class 1. Class 2 is not as dangerous as class 1, but again it is dangerous. So services that are not included in other classes are in class 2. This classification includes the majority of unit process piping and selected offsite piping. The examples of these services are on-site hydrocarbon that slowly vaporize during the release, operating below the boiling point but above the flash point. On-site hydrogen, fuel gas, natural gas. On-site acids and caustics are in class 2. In class 2, thickness monitoring will once in 10 years and external visual inspection will be once in 5 years. So thickness monitoring 10 years, visual inspection 5 years. Next is class 3 pipe. Class 3 is again not going to be as dangerous in class 1 and class 2, but again, it is dangerous but located in a very low activity area. So services that are either flammable but do not significantly vaporize when they are leaked, below flashpoint, or flammable but located in a remote areas and operating below the boiling point are in class 3. Services that are potentially harmful for human tissues but they are located in remote areas may be included in this class. Examples of this are on-site hydrocarbons that do not significantly vaporize, off-site distillate product line to and fro from storage and loading, tank farm piping, off-site acids and caustics, off-site hydrogen, fuel gas, natural gas, and other low-risk hydrocarbon piping that does not fall in the categories of class 1, 2, and 4. Next is class 4. Class 4 piping, so in class 3, thickness monitoring once in 10 years, external visual inspection also will be once in 10 years. Okay, so in table 1, class 3 is once in 10 years and visual is also once in 10 years. Class 4. Class 4 are generally piping that are non-toxic and non-flammable. So services that are essentially non-toxic and non-flammable are in class 4 and as are most utility piping services. Inspection of class 4 is optional and usually based on the reliability needs and business impacts as opposed to the safety or environmental impact. Examples of class 4 piping are steam condensate, air, nitrogen, water, boiler feed water, stripped sour water, dew boil seal oil, ASME B31.3 category D services, plumbing and sewer lines. So all of these are going to be in class 4. So there are 4 classes of piping system which are recommended by ASME 570. Okay. Next, extent of visual, external and CUI inspections. The external visual inspection, including the inspection of corrosion under insulation, should be conducted at an interval no greater than those listed in table 1. So in table 1, CUI inspection is also given. So CUI inspection again in table 1. So this table 1 we use for corrosion under insulation as well. The results of visual inspection should be documented to facilitate follow-up of inspection. For external inspection of the susceptible systems, the additional examination is required. For inspection of corrosion under insulation, the extent and type of additional CUI inspection is listed in table 2. So this is table 2, then it is listed there. The damaged insulation at higher elevation temperature may result in CUI at lower areas remote from the damage. Non-destructive examination of corrosion under insulation should be conducted as listed in table 2 at the suspected locations operating above minus 12 degrees Celsius to 175 degrees Celsius for carbon steel and low alloy steel piping. RT or insulation removal and visual inspection is normally required for this kinds of inspection at damaged or suspected locations. Because in most cases, when you check the insulation in most cases seems fine. But there can be damage below that insulation. For that, insulation removal might be required, or you can simply do RT for this. If the inspection of damaged or suspected areas has located significant corrosion under insulation, the additional area should be inspected where warranted and up to 100% of the circuit should be inspected. So these are the tables. So for class 1, at damaged insulations, approximate amount of non-destructive examination or insulation removal at the areas with damaged insulation. So in this case, 75% of the insulation needs to be removed and non-destructive examination has to be done. At non-damaged areas, 50% of insulation must be removed and non-destructive examination should be done. For class 1, class 2, class 3, class 4, the significant amount of decrease of insulation removal can be seen. For class 4, it is generally optional. It is recognized that several factors may affect the likelihood of corrosion under insulation that include local climatic conditions, insulation design and maintenance, coating quality, service conditions. Facilities with CUI inspection experience may increase or reduce CUI inspection targets of Table 2. An exact accounting of CUI inspection targets are not required. Owner user may confirm inspection targets with operational history and other documentation. The piping systems that are known to have remaining life of over 10 years or adequately protected against the external corrosion need not be included for non-destructive examination recommended Table 2. So any pipe that is having a remaining life of greater than 10 years or if they are adequately protected, then the Table 2 might not be used. Okay. Extent of thickness measurement, inspection and data analysis. CML monitoring. We already know what is CML. CML is condition monitoring location. There are specific areas where inspection needs to be carried out. To satisfy the inspection interval requirements, each thickness measurement inspection should obtain thickness reading on a representative sampling of total number of CML on each circuit. This representative sampling should include data for various types of components and orientation found in the circuit. When general thinning is predicted, the sampling should include various types of component within the circuit. Where localized damage mechanisms are identified, the sampling should also include location, orientation, where the damage is most likely to occur. If RBI is used to set the inspection intervals or due date, CMLs are not required for inspection as per RBI assessment, do not need to be inspected in accordance with the recommended maximum intervals of Table 1. So when RBI is used, check, find out the frequency through RBI. If RBI is not used, then the Table 1 that is given, that should be the inspection interval. Next is analysis. So point-to-point method, in this analysis whereby the corrosion rate, remaining life and re-inspection interval is determined for each individual CML. The future inspections are managed based on the worst case half-life established at each CML. This method can lead to significant or frequent inspections of the same piping systems if they are not carefully managed. Next is circuit analysis method. In circuit analysis method, we'll generally consider one circuit to be more dangerous and accordingly we can identify it. The piping that is properly circuitized into common corrosion mechanism and expected rates, a statistical analysis may be used to determine the representative circuit corrosion rate and inspection interval. There are a number of considerations for a statistical analysis approach that are necessary to remain appropriately conservative. Some of them include approach is generally applicable to damage mechanisms that are uniform and some mildly localized corrosions. Location that exhibits significantly different corrosion rates and locations with shorter remaining life may need to be analyzed separately. Sampling statistics should be considered to check the statistical confidence factor given the variability of the dataset. The number of data points, that is CML inspection, may need to be adjusted to achieve the desired statistical confidence before employing a statistical methodology. A safety factor or a confidence level which may be dependent on the expected damage mechanism may additionally account for circuit complexity and should be considered to account for uncertainties such as measurement error and overall failure risk. CML re-inspection shall not be extended beyond the date projected to reach the established minimum required thickness. Absolute limits should be considered for re-inspection of CML based on the likelihood of failure. As a minimum, the worst case CML within the circuit shall be inspected at the next inspection interval. Again, some data analysis needs to be done. Some level of data analysis is recommended under the both approaches since the calculated corrosion rate used to predict the future remaining life was a product of prior operating history It is important to check any acceleration in the corrosion rate over the time to be aware of the planned operational changes. Good quality management of change and integrity operating window programs are necessary where critical process variables may affect corrosion or damage rate and susceptibility are tracked. So following data might need to be considered. So the measured rate and expected or predicted range, short rate significantly different from long rate corrosion, has variability within the circuit increased significantly over time? Do particular components, orientation, sections within the circuit, or identifiable features of the circuit exhibit significantly different rates? Have data anomalies such been resolved either through a review process or verification reading prior to data analysis? Next is extent on small bore piping, dead legs, auxiliary piping, and threaded connections. Small bore piping. Small bore piping are basically very small piping, generally less than 2 inches diameter. So SBP is a primary process piping that shall be inspected in accordance with the requirements of this document. As with the large diameter piping, the inspection practices for SBP shall take into consideration the damage mechanism that are listed in API 571 other than just wall thinning. When RBI is not used, the SBP secondary process piping has a different minimum requirements depending on the service classification. Class 1 and Class 2 secondary SBP shall be inspected for the same requirements as primary process piping. Inspection of Class 3 and Class 4 secondary piping is optional. At the owner or the user discretion depends upon the reliability and the risk of that SBP. Next is dead leg inspection. Dead leg is basically where the flow is significantly lower or it is halted. Okay, so dead leg include both large bore and small bore pipings and can be the increased corrosion requiring the special attention if they are deemed potentially corrosive or by a corrosion specialist. Because of the accumulation of the contaminated water, solid material, different temperatures from the main line, or accumulation of the concentration of the corrosive species. Risk assessment can be useful in determining which piping system dead leg may be higher threat to accelerated corrosion than active piping circuits. Dead legs that are a part of primary piping system should be considered at a greater risk because of the inability to valve them off in the event of a leak and a higher potential consequence of the larger leak. Infrared thermography may be useful for locating liquid interfaces in the dead legs. The dead leg may be combined into one circuit if their anticipated damage mechanisms and corrosion rates are similar. Inspection should include profile radiography on small diameter dead legs such as vents and drains and scanning UT or RT for larger diameter dead legs. Other examination technique might include EMAT, PEC, profile radiography should be employed in the dead legs that may be susceptible to fouling deposits that could cause the under deposit corrosion and other integrity problems. Auxiliary piping. The inspection of auxiliary SBP associated with the instrument and machinery is optional. Okay, so it depends on the discretion of the owner, user, and the risk assessment. You might do it, you might not do it. The criteria to consider whether the auxiliary SBP should be inspected will be dependent on piping classification, potential for environmental and fatigue cracking, potential for corrosion based on the experience of with the adjacent piping systems, potential for CUI, potential for fatigue, erosion, corrosion, or thermo wells. Threaded connections, inspection and mitigation. The inspection of threaded connections should be in accordance with the requirements listed above for small bore piping and auxiliary piping. The seal weld threaded connections to reduce the likelihood of thread connection failure scenarios may close attention to weld prep cleanliness to avoid the welding defects and cover all threads completely. Sometimes when the threading is done, additional welding is done so that whenever the leak happens, the leak would not go through or the thread failure would not happen. So once the threading is done, the pipe is connected and welding is done so that this thread connections become permanent. The SBP connections associated with rotating equipment, especially threaded connections, are often subjected to fatigue damage. As a result, they should be periodically assessed and considered for a possible renewal with the thicker wall or upgraded joint design. Need for such renewal will depend on several issues: classification of the piping, magnitude and frequency of vibration, the amount of unsupported weight, current piping wall thickness, whether or not the pipe system can be maintained on steam, corrosion rate, intermittent service, etc. Inspection and maintenance of pressure relieving devices. Again, whenever we are talking about pressure relieving devices, always the recommendations are given in API 576. So pressure relieving devices can be tested and repaired by the repair organization experienced with pressure relieving device maintenance. PRD should be inspected, tested, and maintained in accordance with API 576. Quality assurance program. For PRD, each equipment repair organization shall have fully documented assurance program. As a minimum, following things are to be included in the quality assurance manual: title page, revision log, content page, statements of authority, responsibility, organizational chart. So these are the things that are listed, which should be included when making a quality assurance manual for pressure relieving device inspection and repair. Okay. Each repair organization shall also have a fully documented training program that shall ensure the repair personnel are qualified within the scope of the repairs. Testing and inspection of pressure relieving devices. The pressure relieving devices shall be tested and inspected at intervals that are frequent enough to verify that the valves perform reliably in a particular service condition. Other pressure relieving devices, the rupture disc, vacuum breaker valves, shall be inspected at the intervals based on the service condition. The inspection intervals for all pressure relieving devices are determined by the inspector, engineer, or other qualified individual as per the owner user's quality assurance system. Now, pressure testing, PID pressure testing, and pressure relieving device testing and inspection intervals. Unless documented experience or other RV assessment indicate that the longer intervals are acceptable, the test interval should be based and should not exceed 5 years for typical processes and 10 years for clean, non-fouling and non-corrosive services. When a pressure relieving device is found to be heavily fouled or stuck, or when pressure relieving devices fail as a received POP test, the inspection and the testing interval shall be reduced unless a review shows that the device will perform reliably at a current interval. So what is a POP test, when it is to be done, we'll talk about it later on when we go ahead with the pressure relieving device document, that is 576. For now, we just have to understand that whenever you feel or whenever there is an evidence to identify that the pressure relieving device is stuck, fouled, corrosive, then you might need to do inspection, you might need to review it, check it, repair it, or even replace it. Okay. The owner user should define the criteria as a constituent as a received POP test failure. The owner user may define the criteria for the failure based on as received POP test pressure as the percentage of test pressure. The default criteria for the valve being shut are at max 150% of the set pressure, beyond which the valve is classified as a stuck shut. If it does not pop, the test is discontinued. The review should determine the cause of failure or the reasons of pressure relieving devices not operating correctly. When pressure relieving devices are removed for the inspection and testing, the inlet and outlet line should be visually inspected for fouling and plugging. Again, we need to check API 576 for all the details required for pressure relieving device inspection. That was section 6, that was interval and frequency of the piping inspection. In the next section, that is section 7, we'll see how data evaluation is done, how corrosion erosion measurement is identified, what is long-term corrosion rate, short-term corrosion rate, remaining life assessment, etc. Okay, that was all for this video. In the next video, we'll see section 7. Thank you.